This is Physics 1020 and 1090. This is the lecture for Wednesday, April 8th, and we're going to be talking about Chapter 29, Nuclear Physics. And here in this first video, I want to give you an introduction to some of the nuclear concepts and talk about isotopes. First, what I'd like to start off with is a comparison of the atoms and nuclei. See how they're different and how they're similar. And we'll start with mass. The mass of a proton is about 1.7 times 10 to the minus 27 kilograms. Neutrons are roughly the same mass. So protons and neutrons, they may seem like a small mass, but it's actually it's about 2,000 times the mass of an electron. So electrons are almost negligible in mass compared to protons and neutrons. Now remember, the atom has almost all its mass in its central nucleus. So the mass of a nucleus is about the same as the mass of the atom on a whole. The only thing that's missing are these electrons, but the electrons are such tiny mass that they're almost negligible. So mass, atoms, and nuclei are basically the same. In size, we've discussed the size of atoms and nuclei already. Atoms, the Bohr radius for the hydrogen atom was about 0.05 nanometers, or roughly a half an angstrom if you prefer that unit. Whereas nuclei, we found, were measured in femtometers, 10 to the minus 15 meters, or fermis. 5 fermis was a typical nuclear radius. So you see that nuclei are about 1/10,000th the size of atoms. So nuclei are very small objects right at the center of the atom. Well, now let's compare density. Okay, density is mass per unit volume. Atoms and nuclei have roughly the same mass, but the volume is much, much smaller in nuclei. Density is going to go as 1 over the volume, so your volume changes with the cube of the radius. So volumes tend to change with the third power of the linear distance. So if the linear size of nuclei is 1/10,000th of an atom, then the volume is going to vary by 1/10,000 or 10,000 cubed. Or in other words, the density of a nuclei is about 10, this is 10 to the 4th raised to the 3rd, that's about 10 to the 12th times. So nuclei are incredibly dense, much, much denser than atoms as a whole. Now let's talk about energies and energy levels. Okay, in atoms, we found energies of bonds between atoms, or energies of electrons held in atoms, is around 10 to 100 eV. There's a lot of variation. But for instance, in the hydrogen atom, the innermost electron was held in its ground state by an energy of 13.6 electron volts. So this is the order of magnitude. And if these were photons, they'd have energies here, basically in the ultraviolet. Some may be in the visible, mainly in the ultraviolet part of the spectrum. In nuclei, the energies with nuclear objects tend to be much higher, 1 to 10 mega electron volts, or 1 to 10 times 10 to the 6 electron volts. So they're much higher energies that nuclei work at, and if these were photons, that would mean they would have gamma ray types of energies, which are similar to X-rays, but usually nuclear of origin. So you're going to have gamma rays associated with nuclei, where you have visible or ultraviolet light associated with atoms. How about forces? Well, we saw in the Bohr model that the force that holds the atom together is basically electrostatic force. Bohr used the electrostatic force in his F equals ma. So that we studied right at the beginning of the semester. K, the Coulomb constant, Q squared over R squared. Now in nuclei, it has to be different. And how do we know that? Because nuclei contain a bunch of protons. And those protons would be repelling each other. So what holds the nucleus together? Something has to hold it together, and it's the nuclear force. There's yet a different kind of force in addition to the electrostatic force. So this nuclear force, and there's actually 2 versions of it, strong and weak, but we're not going to worry about that for this class. Nuclear forces tend to be very short range. Remember, electrostatic forces fell off as 1 over r squared. That's a rather slow fall off. Nuclear forces fall off dramatically over just a distance of a few femtometers. Nuclear forces tend to be attractive. They're always attractive. So nuclei are attracted, and that's what holds the whole nucleus together, are the attractive nuclear forces. Whereas electrostatic forces can be positive or negative depending on the charges. And that brings up another point. The nuclear force tends to be charge independent. In other words, as far as just the nuclear force goes, the force between holding 2 protons together is the same as the force holding 2 neutrons together. Now, it's true that the protons also have an electrostatic force, which tends to throw them apart. So that may influence the total force and the electrostatic and the nuclear energies. But as far as the nuclear force is concerned, nuclear forces between proton and proton is the same as between neutron and neutron is the same as between proton and neutron. They're charge independent. Now I'd like to talk about isotopes. What are isotopes? Well, to understand isotopes, we need to know, keep in mind 3 numbers, and we're going to be using these all the time throughout the entire chapter. So you need to remember these 3 in order to really understand what we're saying. First of all, there's one that gets the symbol Z and is the atomic number, and that's the number of protons in the nucleus. Remember, the atomic number is what specifies what element you have. So atomic number is probably the most important number that is associated with the nucleus, how many protons it has. N is going to be the number of neutrons. So you have Z protons and N neutrons, and A is basically the sum of those two, Z plus N. It's what's sometimes called the atomic weight, or other times called the mass number. For our purposes, it's the same thing. It's the number of protons plus neutrons. Sometimes we like to say that protons and neutrons are both a type of nucleon. So the total number of nucleons present is this mass number A. So with that in mind, let's look how we specify isotopes. All right, so here's a typical way we would specify an isotope. It has a superscript A, which gives you the mass number. So that's the total number of protons and neutrons, in this case 16. And a subscript Z, which is the atomic number. So it has 8 protons, and if a mass number of 16, you take 16 minus 8, that means it's going to have 8 protons and 8 neutrons, a total of 16 nucleons. And element 8 is oxygen. So we use the symbol for oxygen, O, and that's what's here in this symbol. So I would read this as typically a person would say that's oxygen 16. Realize that Z, the 8 here, and the element symbol O are somewhat redundant because once you know that it's element atomic number 8, you know it's oxygen. However, we generally will include the subscript. So you could just write O with a superscript 16, and people do that sometimes. I'm not going to expect you to have the entire periodic table memorized and remembering what the atomic number is for every element. So I will generally write this in, but realize that if I didn't write it in the subscript, you would know what it is anyways just from the symbol. Now, there are 3 stable isotopes for oxygen. There is oxygen 16, and that's the vast majority of oxygen is oxygen 16. All 99.76% of the oxygen on Earth is oxygen 16. But there's 2 other isotopes of oxygen that's also present. There's oxygen 17. That would be 8 protons and 9 neutrons. Oxygen 17 makes up just 0.04%. And oxygen 18, so 8 protons and 10 neutrons, is 0.2% of the total amount of oxygen. So we say there's 3 stable isotopes for oxygen. And really, the atomic properties, the properties involved in chemistry, are pretty much the same for all the different isotopes of oxygen. It's just that some of the physical properties that would depend on the mass of the atom could be slightly different between the different isotopes. By the way, with this element symbol, if you don't know what the element symbol is, you need to get yourself a periodic table. In fact, I suggest that for the rest of this chapter, and really the rest of the semester, you go out, you find yourself a periodic table that you can keep at your side. For instance, here's the one in our book, The Making of the Atomic Bomb. It at least should have the atomic, oops, oh no, let's come back. Here I am. The atomic symbol, and the atomic number, which is the number on top, and the mass number. Well, actually what's written in the periodic table is not the mass number itself. It's sort of a weighted average of the mass numbers. For instance, if you look at oxygen, the number down there is 15.9954. Well, that's because the vast majority of oxygen is oxygen 16, but there's a little bit of oxygen 17 and 18, and there's also some slight discrepancies between the exact weights of these. So what you get is, on average, the mass number is 15.9994, but you would find that if you want to specify certain isotopes, they'll always just be integers. Okay, so let's talk a little bit about nuclear stability. Now, you have a very nice figure in your book, figure 29.3, which will repay a lot of study. But it looks roughly like what I'm showing here. What you have is a plot of a number of neutrons versus number of protons. And you can have essentially a nucleus with any number of neutrons and protons, but the stable ones are roughly along this curve here. And there's two effects that determine how stable, where are the stable nuclei. The first effect is that nuclei like to have the same number of neutrons as protons. So this dashed line is the line that gives you n equals z, the same number of neutrons and protons. And that arises because of an effect based on the Pauli exclusion principle, which is a quantum mechanical effect that we won't really talk about. But in general, this effect dominates for the lighter atoms or nuclei. So down here at the lighter nuclei, they generally have the same number of protons and neutrons. However, when they get heavier, you're packing more and more protons into the nucleus. And the protons, remember, are all positively charged and they repel each other. And that makes them less stable. And the neutrons aren't charged, so there's no electrostatic repulsion among neutrons, but they still have that same nuclear force binding things together. So you can think of the neutrons as glue that holds everything together. So as you get up to the higher atomic numbers, you need more of that glue because there's all that electrostatic repulsion, and the number of neutrons goes up above what would be an equal number of neutrons and protons, just because you need the glue. So let's see some examples. Down here for their light nuclei, examples are, for instance, helium-4. Helium-4 has 2 protons and 2 neutrons. Carbon-12. Carbon-12 has 6 protons and 6 neutrons. Oxygen-16, 8 protons, 8 neutrons. These lighter elements have equal numbers. In fact, the heaviest element that has equal numbers of protons and neutrons is calcium-40 with 20 protons and 20 neutrons. Above calcium-40, there's no other stable nuclei that have n equals z. At the heavier nuclei, they all have more neutrons than protons. They're neutron rich, and it gets to be a considerable effect at the very heavy nuclei. Now, there's another feature, I'm not sure this is discussed in your book, about magic numbers. Now, if you remember in atomic properties, you have the periodic table, and as you fill electrons into these different shells in the atom, you eventually can fill a shell, and that's a particularly stable atom. For instance, the noble gases, helium and argon and the like, are particularly stable because they have a full shell. Well, there are similar types of shells in nuclei. You could solve them using quantum mechanics. And it comes out that there's certain nuclei that have filled shells that are particularly stable. And these number of nuclei in these shells are called magic numbers: 2, 8, 20, 28, 50, 82, and 126. So if a nucleus has either a number of protons or a number of neutrons equal to a magic number, it should be fairly stable. For instance, here's helium-4, 2 protons, 2 neutrons. It's doubly magic. It's got both neutron and proton number is 2. So that means the helium-4 is a particularly stable nucleus. Remember I told you calcium-40 was the heaviest nucleus that had N equals Z? Well, calcium-40 is stable. One reason is because it's doubly magic. 20 protons, 20 neutrons. So calcium-40 is not too surprising that all the nuclei around it might be unstable, but 2040 for calcium was actually stable. Now, different elements can have different number of stable isotopes. Oxygen, we saw 3. What element has the most stable isotopes? Well, that element turns out to be atomic number 50, and the symbol is SN, and you might not realize it just from this atomic symbol, but that's tin. So tin is SN. It's based on some Latin or Greek name for tin. It has 10 stable isotopes. So you get, and it's not too surprising because the number of protons is a magic number. So it's not too surprising that you get a lot of stable isotopes because it's partially stable because of the magic number. But 10 stable isotopes is rare. You don't usually have that many, but you can have quite a few stable isotopes. You can also have elements that have no stable isotopes at all. One example is atomic number 43, technetium. Technetium is one of those holes in the periodic table that Moseley found. You have no stable isotopes of technetium. So before people started doing nuclear experiments, there was basically no technetium to be found on Earth. The only place we really find it in enough amounts to study nowadays is in nuclear reactors, which we'll talk about in the later lectures, where it gets produced, but then it decays away with time so that eventually, when it was formed with the Earth, there may have been a little bit of technetium, but it quickly decayed away, and there's no technetium around now that's naturally made. All right, well, as nuclei get very heavy, they become less stable. So you might ask, what's the heaviest stable isotope? Turns out the heaviest stable isotope is bismuth-209. Has 83 protons, and if you take 209 minus 83, that's 126 neutrons. 126 is magic. So it's not too surprising that bismuth-209 would be stable when some of the other nuclei with close atomic numbers and masses aren't, because this has this magic property. But recent experiments have indicated that bismuth-209 may actually not be truly stable. It decays, but it decays so slowly that its half-life, and we'll talk about half-life in the next video, its half-life is much longer than the age of the universe. So for all practical purposes, bismuth-209 is stable. Now, if you look at the element next to it, element 82, which is lead, lead-208 is doubly magic. Has 82 protons and 126 neutrons. So lead-208, it's not surprising, is one of the more stable isotopes. And a lot of the heavy stable isotopes will decay down into lead. So realize that all isotopes of lead are magic in their proton number. It's just only 208 is doubly magic in its neutron number. So lead, you can take just a rule of thumb, the heaviest element that you're going to be able to find that's abundant and is absolutely stable is basically lead. Now, one more property of nuclei is that nuclei that have an even number of neutrons or an even number of protons are slightly more stable than elements that have an odd number of neutrons or protons. So again, lead-208 is a particularly stable nucleus. It gets a little bit more stable because of this odd-even effect. It's a really small effect, but we'll find that it's important in one particular case that we're going to look at in uranium. Finally, I want to talk to you about binding energy of nuclei, and that's another nice figure in your book figure 29.4, which I've very roughly sketched out here. What I'm plotting is the binding energy per nuclei. So the more binding energy, the more tightly that nucleus is held, and the more stable the nucleus is. Now, I didn't want to talk about the total binding energy because that depends on how big the nucleus is, how many nucleons there are. So we divide out by the number of nucleons, or binding energy divided by A. So it's binding energy per nucleon, and this is in mega electron volts. That's the scale for energies in the nucleus. And what we see, and we plot that now as a function of A, the mass number. And what we find is that there's two effects. For very large nuclei, there are a lot of protons present. So many protons that there's a lot of electrostatic repulsion, which opposes the holding of the nucleus together by the strong force. And that tends to make the binding energy smaller than if you had a smaller number of nucleons. So it goes down at very large atomic mass numbers. It also goes down at very small atomic mass numbers, and that's kind of surprising, but that's what's called a surface area effect. That is, what you like to have is you like to have your proton and neutron completely surrounded by other protons and neutrons. A bunch of neighbors, so they all are holding it tight and it's as stable as possible. So you have deep inside the nucleus, your protons and neutrons are all surrounded by other protons and neutrons, and that's great. But near the surface of the nucleus, you might have a proton and neutron that's held by some of its neighbors down below, but it's on the surface. There's no holding above. So that means the surface neutrons and protons aren't held quite as tightly. So you get this surface to volume effect here, where nuclei on the surface aren't held as tightly as nuclei deep in the volume. For instance, think about helium-4, 2 protons, 2 neutrons. No matter how you put those together, it seems like all of them are on the surface. There is no deep protons and neutrons completely surrounded by others. So it's got a lot of surface area for a given volume, and it means it's going to have a very lower binding energy. This effect goes away as you get more and more neutrons and protons. That's just because the number of neutrons and protons deep in the volume grows more quickly than the number on the surface. But you also get this effect from the electrostatic repulsion. And that means that right up here is going to be where the most stable nuclei are. And that's going to be, for instance, the most stable nucleus of all is going to be nickel-62. Nickel-62 has 28 protons, and if you remember, 28 was one of our magic numbers. So nickel-62 is a particularly stable nucleus. And it's thought that eventually, someday, after eons of time, all the nuclei will eventually decay or change until they go to their most stable state, and you'll get mostly nickel. Iron's also right up here near the top. So nickel and iron tend to be among the most stable of nuclei. And when you get heavy nuclei, they can get more stable by breaking apart, and a very light nuclei can become more stable by fusing together. So that's the binding energy. Now, what we've talked about mostly are stable nuclei, but also nuclei can be unstable. So in the next lecture, we're going to talk about nuclear decay, and in particular talk about the concept of a half-life.